So in this one, let's design a rate limiter. The motive of this system design is to understand that more boxes does not mean better systems. I have seen at so many places people overcomplicate by drawing services of this box, that box, adding load balancers as random places. That's not how real systems are built. We'll keep it extremely realistic whenever we are designing any system, right? Through this, we will understand different kind of trade-offs that we make and understand how we are making scaling decisions. Something really fascinating is up our sleeves. Okay, so what is a rate limiter? So system typically breaks down when you put in tremendous load on it, right? So that is where we need to ensure that that doesn't happen. Otherwise, if our system is down, we would have an outage that would be lost in revenue. No one would be happy. So what the way to safeguard ourselves from having to serve tremendous load is to add a rate limiter. So rate limiter's job is to limit the number of requests in a given period. Like, hey, that I would only allow 1000 requests per second. Anything more than that, I'll discard. That's the job of a rate limiter. Right? Now, what we would want is we would want to limit the number of requests to some configuration. That's number one. Second is we would want to allow developers to configure a threshold at a granular level. Now, this is interesting. Whenever people are designing rate limiters, it's not like, let's say you have a backend service, right? Some code written in Python, Java, whichever language you are comfortable in. And what typically happens is in the REST request handler that you write at the rate app and the routes that you define, on top of it, you would want to just add a simple annotator that, hey, this API needs to be called or needs to be allowed to be called 100 requests per second. Anything more than that, you can safely discard. Now that's a granular level at which we would want people to be able to configure it, right? And third, it should not add a massive additional overhead. This is one of the most important realistic requirement from the system, that hey, if checking the rate limiter itself becomes slow, if it becomes expensive, the overall response time gets affected, because for every single request you would be typically consulting rate limiter that, hey, should I go on, should I move on or not? If not, I'll drop myself. Correct? Okay, given the requirements that are clear, now let's understand a bit more about rate limiter and then we start designing it. Okay, so rate limiter is the first line of defense. So any incoming request would first be consulted to a rate limiter that, hey, am I allowed or not? If rate limiter says no, it basically kills that request right away. Otherwise, if it says yes, then you move ahead, right? That's the job of rate limiter. Okay. What happens when you breach it? Let's say an API was allowed to call 100 requests per second. You hit that. What happens after that? So rate limiter, if it's an HTTP thing, your rate limiter typically rejects the request with an HTTP status code 429. Right? That's the thing. 429 is the status code, which means too many requests. So whenever, and it's a very good practice to return the correct status code. You could also return 200. No one's stopping you from doing that. But instead, it is always better to follow the conventions set. Use this response status code of 429, which denotes that, hey, there are too many requests coming in. Correct? Okay. Now let's understand where rate limiter fits into the system. We go step by step into building any and every system, right? Okay. So let's understand where does a rate limiter fit. Now, for example, in your architecture, there is a front-end proxy. It's just a fancy word to say that all incoming request has a single point of entrance. Could also be a load balancer, not denying it, right? Maybe Nginx, maybe HA proxy, something. If there exists a front-end proxy through which all the request comes in. So now what you can do is you can make this front-end proxy talk to rate limiter and see if it is allowed or not, that request is allowed or not. If not, you send 429 as a response right here and then. So which means the request does not even come to your backend service. Let's say you're trying to protect your authentication service, or rather, let's say you're trying to protect your payment service. This is your payment service, right? Because you're trying to protect it. And if you have a front-end proxy, the request comes to front-end proxy checks the rate limiter, rate limiter says no, you cannot move forward, it immediately responds back with 429 to the user. The request is not even coming to the backend, the payment service at all, right? This is one place. Second way to implement this is something like this, where you don't have a single point of entry, but let's say you have your payment service, you let the request come to your payment service, and then payment service checks the rate limiter. The first thing, you may write it in your middleware, right? In your application logic, web server, whichever framework you're using, there is typically a provision to add a middleware. What is a middleware? Middleware is any piece of code that executes before your actual handler is invoked. That is a middleware. So when you get the request, before your actual handler is invoked, you invoke another piece of code, right? Just Google search about middleware in case you are hearing it for the first time. So you can write in a middleware so that you don't have to make changes every place. So when as part of the handler, what you do, so the request comes to your service, your payment service. The first thing your payment service does is checks the rate limiter that, hey, am I okay? Like, is it too many requests or not? Am I allowed to process this request or not? Your rate limiter says yes, so then payment service processes it, right? If your rate limiter says no, payment service immediately returns a response of 429 to the user, right? These are two different places where you are placing the rate limiter. First, where a proxy interacts with it, if you have a proxy. If not, then your load balancer forwards the request to your service, or maybe an API gateway forwards the request over here, and the service talks to rate limiter and then makes that decision, right? In this approach, the second approach, the request at least comes to your service, and then your service says to either accept or discard. In the first case, your request does not even come to your service at all. Pick one over other. In case you have proxy, you can pick the first one. You don't have proxy, you want it simplified, you pick the second one, right? There is no one way to build a system. It's all filled with trade-offs. Okay, fine. Now let's dissect a rate limiter. Now that we understand where rate limiter fits into the scheme of things, let's dissect. We'll go with simple approach. That rate limiter needs to track the number of requests that you are allowed to serve in a given period of time. So which means that you need to keep count of number of requests that you have served up until now. As soon as period gets over, that counter should reset. Simplest algorithm to start with. This algorithm is called as fixed window algorithm. That in a particular window, you are allowed to handle n requests per second. You keep a track of number of requests that you have served. When you are within those limits, good enough. If you are not within those limits, you don't serve those requests, right? As soon as period gets over, you reset your counter. This is fixed window algorithm. We would just try to understand. That's the simplest to start with. We'll not overcomplicate, right? Okay. So what we are doing? What we are doing over here is, for every incoming request, we would be updating the database, right? Because we would have to register that, hey, I'm handling one more request, one more request, one more request. So your database is constantly being updated for every request that you handle. Number one. Number two is, for every incoming request that you're getting, you're also reading from the database that, hey, am I allowed to go on and serve this request or not, right? Third, we need an ability to clock the time, which means somehow we need to measure that we are beyond this, some sort of expiry, if we may put it, right? So here you would have observed that instead of directly picking a database, we first understood what kind of support, what kind of queries we are firing or we will fire in the database, depending on which we make a sane decision of which database we would go for, right? Okay. Now let's say our rate limiter limits per user, because it limits per user, one user is allowed to make only n requests per second, hypothetically. So we store the number of requests that the user served in a given period of time, right? Then once the period is over, we reset the counter. Now resetting the counter is almost equal to setting it to 0, which is equivalent to deleting that key. So what we are looking for is a key value store with expiration. Key value store with expiration, fast, because we are doing it for every request. Redis comes to our mind, right? So that is where what we do is we pick the Redis database to store that this user up until now has handled these many requests, and now once the timer is over, the expiration hits, the key would be automatically deleted. Next time when you do count plus plus, it would start from 1 automatically. Right? So this is how you would use Redis to build a simple fixed window algorithm. Right? Okay. Now, what about checking and updating? Because we would need, for every request that is coming in, we would need to check and like someone needs to talk to Redis to see if I'm allowed or not, and to see, hey, please, I'm allowed, so please do count plus plus. Correct? Someone needs to do that. So there are two ways to build it. First is where you'd say, hey, let me put a rate limiter API server, and I talk to rate limiter, which talks to Redis and gets the counter and updates the counter and whatnots and sends back me the response. That is first way. Second way to do this is you say, no, let my API server or my proxy directly talk to database. This is very counterintuitive, but very efficient because you save a network hop. This is what I wanted to highlight from this design, that just drawing boxes for the sake of it does not make any sense. Right? Okay, let me explain. So here what we are doing is, let's go with the first approach and add an API server for the rate limiter, which means this is your rate limiter, which is storing the number of requests served in Redis, right? And either your front-end proxy or your API server, however you have defined, talks to this rate limiter, right? But the way you talk to this rate limiter will be through this API server. Obviously, there would not be just one rate limiting server. You would have multiple of them, and you would have a load balancer to balance the load between them so that it becomes the only point of entry. So now what you are doing is, this becomes your architecture. But if you look carefully, this is adding a substantially large number of network hops, because now what would happen is, request from a user comes to your front-end service talks to this load balancer forwards this request to API servers, rate limiters API server, rate limiters API server talks to Redis, get those things, send back the response, back the response, and now it is allowed to serve the request. So now the request is sent to payment service. You see how slow this process is? The number of network hops just increased. You don't want that, because now it breaks the condition that we had, that it should not add a massive additional overhead. Here, by going via this route, what has happened is you are adding a massive additional overhead, massive number of hops of network to reach to this database and get things done. And because for every single request, you would have to consult this rate limiter, it would amass, it would add up to a lot of network delay. It would shoot up your latencies like anything. Okay, so what's the way out? You remove things you don't need. The idea is that, hey, let my front-end proxy or my service directly talk to Redis. I don't need any API server. I don't need anything to do it. Let the business logic reside on the proxy or my payment service. Now with this you would say, oh, would I need to duplicate the logic? Yeah, but make your rate limiter a library, not a service. So for example, for your organization, you create a rate limiting library, not a service, but a library, because at the end, what this API, what this rate limiter's backend server or API server was doing, you take that piece of code, because at the end it's all about manipulation of these keys, right? Doing count plus plus and whatnot. Take that piece of code, create a library and put it over here in your proxy or on your payment service. When the request comes in from this library itself, you're directly manipulating the database. No need to add additional network hops, because at the end, what you need to do in order to implement a fixed window algorithm, you just have to do count plus plus every time and set an expiration. That's all you want to do. You can just do it with library. You don't need to have a service. So now your rate limiter service is now just reduced just one database. This is real world system design. This is how systems are built in real world. You think of every single overhead that comes your way. Keep things really simple, right? Okay. So now here what we did is, now our rate limiter quote unquote service is now just reduced to this one database and a bunch of library code that is included in any service, that let's say payment service may you install that library and you start invoking it. Maybe a pip package or anything like that. Node.js, may you create a node package and whatnot and import and start using it, right? Same thing with Java, same thing with anything. Similarly, you can make those changes in the front-end proxy as well. Correct? Okay. This is what realistic system design looks like. But now if you look carefully, you still need a way to, scale this part. Because this is just one machine. How would you scale it? It's very important to scale it. So let's talk about scaling a rate limiter. Given that now a rate limiter is now just boiled down to a database, scaling rate limiter implies scaling this database. So we know 3 types of scaling for a database. First is vertical scaling. Can we vertical scale to handle more load? Perfect. We can do that. So long as you are able to handle it, vertical scale your cache, like vertically scale your Redis database. Not really a good idea to call it a cache because it is actually the source of truth. So just vertically scale your Redis up until the point that you are happy with it. Superb, that works. Second way to do it is add read replicas. Can we add read replicas? We don't need to, because this is not a read heavy traffic. What you are doing is, for every single request that is coming in, you are actually writing or updating Redis, because you are doing count plus plus every time. So this is not a read only traffic or read heavy traffic, which means adding read replicas will not make any sense, right? So that is not a good way to be able to handle large load, because if it was read heavy, then adding read replicas makes sense. Otherwise it does not. So what's the third way? Sharding. So when you go beyond a certain stage where one node is not able to handle it, you need multiple nodes to handle it. So can you shard it? If you look carefully, because we are rate limiting, let's say per user or per IP address or per access token, it's very key value-ish. You would never need to do cross shard queries. So it clearly indicates that what we can do is we can shard this database and add as many as we want to handle the load. And now it's responsibility of this library to make request to the corresponding shard that exists. It's the responsibility of this library, to be honest, to do that, right? So now we are making an assumption that this library knows how many Redis nodes do we have. Where would it know that? This becomes a single static entry in your rate limiter service. Let me draw it neatly. This becomes maybe a database, some simple entry, maybe a file on S3, something. One common place which holds that these are the servers that I have which needs to talk to. And your library will talk to that when it will talk to that periodically, right? And get these things done. So the flow is really simple. Now what would happen? Request from user comes in. No, let's start from the beginning. Let's say I start my payment service, right? Now when my payment service starts, when this library loads, the rate limiter library loads, the first thing that my rate limiter library would do is it would talk to this central configuration, which holds the IP addresses of the Redis servers that we have. 3 Redis servers we see in the diagram. It would have IP address of the 3 Redis servers. It would take the IP address of these 3 Redis servers and would create connection with all 3 of them, right? Similarly, if you are doing load balance, if you're doing rate limiting at your proxy side, this would also create connections over there, right? Okay. Now, when the request comes in from the user, depending on what your strategy is, let's say you do it at user ID level. So this would know the user ID that is making the call. Once this knows the user ID making the call, it would pick one shard where it would need to fire the request. How would it know? Let's say simple hash based strategy, right? You would hash the user ID, do a mod 3, you would get one of this IP address, you go to that corresponding machine, get and set and count plus plus and whatnot, do on those instances and do your rate limiting stuff there, right? Here what we are doing is we are just not required a service, just a small database and a small configuration file does the job, right? Extremely realistic system design, right? This is how you would rate limit it, right? So upon every request, you are always doing count plus plus in the Redis database that you have. but to which database would you go to would come from the routing strategy that is defined over here, hash based routing that you typically go with. You hash the user ID with mod 3, you get an IP, you pick a particular machine, you go to that because you would have connection, your library would have connection to this, get the response, send it back to the user, right? So rate limited or not, you do that actual thing, right? Okay. That's how your rate limiter would work. Now let's do some basic mathematics that, hey, how much of storage would we need? Let's say our rate limiter supports rate limiting by user ID. So what you need to store is you need to store user ID and count. Count is an integer. So let's say 4 bytes. User ID is an integer. So 4 bytes, total 8 bytes. Then you may also want to rate limit on IP address and count. That is, from one IP address, I need at max these many requests. So IP address is, let's say, 16 bytes. 16 bytes plus 4 is 20 bytes. Otherwise, let's say you may want to do it at the authentication token level. Let's say authentication token is 16 bytes. So 16 plus 4 is 20 bytes is what you are storing per entry on Redis. So if let's say you have 100 million users and your each entry is 20 bytes long, your total size would be 200 MB, which is equal to 2 GB. So actually, if you look carefully, storage is not the problem over here. You are sharding because the amount of queries you are firing on these databases is huge. So storage is not the problem, compute is the problem, because every time for every incoming request, you are doing count plus plus. And then after every unit of time or after every period of time, that key resets to 0. So compute is the problem, not storage, because of which we would have to shard this database, right? Okay, always keep this thing in mind, that why are we solving a particular problem rather than just solving it for the sake of it, right? And a simple crunching of numbers would help you make that decision really well. Okay, now if you look carefully, this is our functional rate limiter without a doubt. But just to take it up the notch, what we add is we add an admin console that gives you nice visibility on how this rate limiter is performing. For example, total number of unique users, how many have been rate limited, those kind of metrics. Where would you visualize it? Let's say you would want to explicitly allow some user. It's a hack, right? It's a backend, it's a backdoor that you have created to just allow some sort of users and to manipulate your system. So what you do is you define an admin service, a simple front end, which directly talks to this database, maybe via a set of APIs, but it talks to this database. This is your entire admin service, your front end, your back end, everything hosted in a simple Django server or something. And your company's internal developer is allowed to talk to this and manipulate the keys and the values over here, right? So simple admin service to do that management. And this completes our rate limiter design. Extremely realistic, extremely performant, right? So we chopped down those rate limiter and API servers and whatnot to talk to over here. This is, we just added just to get the transparency and visibility and backdoorness, quote unquote backdoorness in your system. The idea being that you should know how to manipulate that. Like a company's internal developer, product manager should be able to manipulate the rate limits in case they want to, right? So a small admin interface that anyone can like anyone in the company can access to and manipulate the rate limiters over here, right? And this is how you design a rate limiter. If you look carefully, this admin service is a very low throughput service. Number of times developer access it, let's say 10 or 15 times a day, just 10 or 15 requests per day. It's not that huge, right? So chill. This is not a very scalable, like you don't need this to be ultra scalable, this admin service to be ultra scalable. Just one server running your backend and front end together, normal Django server does your job, right? Okay, so this is how you would design a very realistic API rate limiter. Here, one thing that I did not touch upon is different rate limiting algorithms. So what I want all of you is to explore, first of all, explore the 3 most common rate limiting algorithms. First is leaky bucket, second is fixed window, third is sliding window. So what we spoke about, that for a given window we are doing count plus plus, after the time expires we delete that is fixed window algorithm. So that is the idea of fixed window algorithm. So what I want all of you to do is to read about fixed window algorithm, sliding window algorithm and leaky bucket algorithm, and more importantly implement them on Redis. Write that code that does that, because when you write that code you would have a very detailed understanding of how API rate limiter works. that algorithm works, because at the end that is exactly what a piece of code that you would write in this library, because you don't have a service. This library is doing that for you. So this library would have, depending on the algorithm, this library would do the sliding window and the fixed windows and whatnot of the world, right? So I want all of you to understand how these algorithms, what these algorithms are, how to write them and implement them with Redis. This way you'd have a very detailed understanding of this building any end-to-end API rate limiter, right? Do that. You'll have quite a bit of fun doing it and implementing it, right? And yeah, this is all what I wanted to cover in this one. I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you the next one. Thanks.